You can have the most powerful compressor in the world, aggressively pumping refrigerant through your system, but it will never drop the temperature of a room by a single degree unless you have a mechanism to eject that heat. That mechanism is the condenser. It operates strictly as a specialized heat exchanger, engineered with a single objective: continuous heat rejection. To understand the load placed on this component, we have to look at the energy it processes. The first source of thermal energy arriving at the condenser is the sensible heat absorbed from the conditioned room itself. The second source is mechanical. As the compressor pressurizes the refrigerant, friction and mechanical work add a massive amount of heat directly into the vapor. The condenser must process both loads simultaneously. The sum of the room's absorbed heat and the compressor's mechanical heat is the exact reason the outdoor unit becomes extremely hot to the touch during operation. If this combined thermal load is not successfully rejected to the outdoors, the refrigerant cannot transition back into a liquid. The expansion valve starves, and the entire cooling cycle instantly stalls. System cooling capacity is not determined by how much cold air an indoor fan can blow. It is dictated entirely by the condenser's efficiency in driving a continuous thermodynamic phase change in the outdoor unit. To trace that phase change, we follow the refrigerant as it leaves the compressor and enters the condenser. At this point, it is a high-pressure, highly volatile vapor, typically sitting between 70 and 90 degrees Celsius. This split-screen chart illustrates the exact thermodynamic sequence. On the left is a pressure enthalpy diagram tracking the system states, and on the right is a cross-section of our condenser pipe. Heat transfer begins instantly because the 90-degree refrigerant is vastly hotter than the ambient outdoor air or water. Step 1 is desuperheating. The sensible heat drops rapidly as the vapor rejects energy, but the physical state of the refrigerant remains a gas. Step 2 brings the refrigerant into a saturated vapor state. We reach the exact temperature where the gas begins to yield, and liquid droplets first form on the inner walls of the pipe. Step 3 is the core phase change. The remaining latent heat is stripped away until the vapor undergoes full conversion into a liquid state. Step 4 completes the process through subcooling. We cool the liquid below its boiling point to ensure absolute stability before it leaves the condenser block. Look closely at the top line of the diagram. This entire 4-step phase change must occur isobarically. We are removing immense amounts of heat, but the horizontal line shows that the high pressure remains perfectly constant. Maintaining that constant high pressure is a mechanical mandate. The expansion valve relies on that pressure to force the liquid refrigerant through its tiny orifice. If pressure drops inside the condenser, the valve loses its driving force. The condenser's sole thermodynamic objective is to extract enough heat to achieve subcooling without sacrificing mechanical pressure. To translate this strict thermodynamic rule into physical engineering, we have to look at how we accelerate that heat transfer in the real world. This 3D cross-section shows the primary material choice: copper tubing. Copper is selected for its supreme thermal conductivity, allowing heat to rapidly radiate outward from the refrigerant, while possessing the tensile strength to withstand high internal pressure. But a bare copper tube faces a severe geometric limitation. It simply lacks the total surface area required to dump heat into the surrounding air fast enough to sustain the cooling cycle. The solution is to press tightly bonded aluminum fins over the copper. By an order of magnitude, aluminum is paired with copper because it provides the necessary thermal conductivity to pull heat away from the tubes, while keeping both the total weight of the unit and the manufacturing costs low. However, a standard copper and aluminum coil fails rapidly when exposed to environmental constraints like corrosive chemicals or salty marine air.
In heavy-duty industrial applications, engineers use stainless steel or carbon steel. These materials sacrifice raw thermal conductivity to prioritize durability and structural survival in harsh environments. For marine chillers operating on ocean vessels, titanium is the ultimate material choice, providing absolute resistance to seawater corrosion. Every physical condenser is constructed as a calculated compromise between achieving maximum thermal conductivity and surviving its specific operating environment. When we look at commercial scaling, the air-cooled condenser is the global standard for residential split systems, window units, and VRF architectures. They require zero water connections and demand low maintenance. Their major limitation is that extreme ambient heat severely limits their efficiency, as the temperature gap between the hot refrigerant and the hot outside air narrows. When air cooling becomes insufficient for high-capacity applications like massive hospitals or data centers, engineers scale up to water-cooled systems. The physics rationale is straightforward. Water is a significantly denser medium than air. It can absorb and transport large volumes of thermal energy much faster. This diagram outlines the shell and tube architecture, the backbone of industrial water chillers. Cold water flows continuously through the internal tubes, while hot vapor refrigerant floods the surrounding outer shell cavity, transferring its heat into the water. For medium capacities, where a smaller footprint is needed, scaled-down variants like shell and coil or double-pipe condensers offer similar liquid-to-liquid heat exchange while being easier to clean. In modern, highly compact applications, we use plate condensers. This exploded view illustrates alternating channels where refrigerant and water flow closely past each other, separated only by thin, corrugated stainless steel plates. The corrugated geometry forces the fluids into a turbulent flow, churning the liquids to maximize heat exchange in a fraction of the space required by a traditional shell and tube design. For environments like large-scale cold storage and industrial refrigeration, evaporative condensers provide a highly efficient hybrid solution. By spraying water directly over the hot coils while forcing ambient air across them, the system utilizes the massive energy required for rapid evaporation, stripping heat away from the coils instantly. Whether it is a dense plate exchanger, a water shell, or a traditional air coil, the architectural design is dictated strictly by the required thermal load and the physical properties of the chosen cooling medium. When a system goes down, nearly all condenser failures share the exact same root cause: a physical inability to reject heat. In an air-cooled unit, blocked or dirty aluminum fins act as a thermal blanket, aggressively trapping heat against the copper tubes instead of dissipating it. Returning to our pressure enthalpy chart, we can see the domino effect. If the heat remains trapped, the refrigerant cannot fully condense. To compensate, the internal pressure spikes dangerously high, shifting the condenser line violently upward on the y-axis. This high-pressure state correlates to symptoms technicians observe: abnormally high head pressure, excessive electricity draw, and rapid compressor overheating. The equivalent failure in water-cooled systems is scaling. Over time, heavy mineral deposits build up inside the water tubes. This mineral scale acts as a hard insulator. It destroys the condenser's approach temperature, blocking thermal transfer and causing high-pressure systemic failure, just like dirty fins. Preventive maintenance, cleaning air coils, verifying fan motor speeds, and treating cooling water is rarely about fixing broken parts. It is the active preservation of the system's precise thermal geometry. The condenser is the absolute arbiter of system capacity. By mastering its thermodynamic limits, material constraints, and physical architectures, a technician ensures the entire refrigeration cycle continues to breathe.